Imagine the world around you suddenly flickering and dissolving like a failing digital simulation. You look at your phone, trusting it to guide you. But without a single discovery made over 100 years ago, your global positioning system would drift by 11 kilometers every single day. Have you ever wondered if the very fabric of your reality is merely a veil hiding a much deeper, more complex mathematical truth? What if time is not a constant heartbeat of the universe, but a flexible thread that stretches and bends depending on how fast you move for centuries? We believed the universe was a rigid machine, governed by absolute laws that never wavered. We saw space as a fixed stage and time as an arrow that flew at the same speed for everyone, everywhere. But at the dawn of the 20th century, a young man sitting at a cluttered desk in a Swiss patent office began to see the cracks in this ancient foundation. He looked at the blueprints of the modern world and realized that our common sense was lying to us. This is the story of Albert Einstein and the most profound shift in human understanding. It is a journey from the chaotic flickering of a digital grid to the majestic, light-warping shadows of a massive black hole. We are about to step behind the curtain of the physical world to witness the birth of a reality where space and time are no longer separate, but are woven together into a single, breathtaking masterpiece. To understand this mystery, we must first look at the way we perceive motion and the fundamental truths of our world. Imagine a vintage steam train moving at 100 kilometers per hour. If a passenger tosses a ball forward to someone standing on the tracks, that ball appears to move at 120 kilometers per hour because the speeds of the train and the ball combine. This is the world as we have always known it, where motion is relative and follows simple logic. However, as we push toward the extreme edges of reality, the laws of physics begin to ripple and distort in ways that defy our intuition. Imagine yourself inside a sleek spaceship, traveling at half the speed of light. You reach out and switch on a flashlight, projecting a beam into the dark cosmos. Under the old laws of physics, that beam of light should be traveling significantly faster than light emitted from a stationary source. But the universe refuses to allow it, whether you are standing perfectly still or racing through the stars at incredible velocities. Light always maintains a constant speed of exactly 300,000 kilometers per second. This unchanging pace acts as a glowing golden barrier in space, a universal speed limit that no physical object can ever penetrate or surpass. It is a single point of absolute truth that remains pure and constant. Even as the camera of our perception races forward at high speed, if the speed of light is the only thing in the universe that never changes, then something else must be willing to bend. In the world of classical physics, space was a rigid, unmoving stage, and time was a steady, rhythmic ticking that everyone experienced exactly the same way. But Einstein realized that for light to always travel at 300,000 kilometers per second, time itself must be flexible. Imagine a translucent silk fabric floating in a void, representing the union of space and time. When an object begins to move at extreme speeds, this fabric stretches and undulates like waves on an ocean. This leads us to a conclusion that sounds like science fiction time dilation. Imagine a pocket watch floating in the deep reaches of space. As it approaches the threshold of light speed, its hands no longer tick with the same urgency. From the perspective of a stationary observer, those hands begin to move in extreme slow motion, as if the watch is submerged in a thick, invisible syrup. But it is not just time that changes. A long spaceship racing toward the stars would visibly flatten and shorten like an accordion as it nears the speed of light. This is not an optical illusion, but a fundamental change in physical reality. The old marble statues of ancient philosophers are crumbling because the rigid, clockwork universe of the past has been replaced by a reality that is fluid, strange, and breathtakingly dynamic. To truly understand how this flexible time changes the human experience, we must look at one of the most famous thought experiments in all of science, often called the twin paradox. Imagine two friends, identical in age and spirit, standing on a futuristic launch pad. One decides to remain on Earth, while the other climbs into a high-tech cockpit, destined for a distant, glowing star. As the engines roar to life, the traveler begins a journey across the vast cosmic ocean, moving at a significant fraction of the speed of light. Inside that cockpit, everything feels perfectly normal. The pilot breathes, moves, and thinks just as they always have, When they look at their digital mission clock, it shows that exactly 2 years have elapsed since they left home. To the traveler, this was a long but manageable voyage. However, as the ship descends back toward a futuristic Earth, the landscape outside the window looks hauntingly unfamiliar. The city skyline has grown taller, the technology has transformed, and the environment has advanced by 2 full decades. The most heart-wrenching moment occurs when the traveler finally steps off the ship. They meet the friend they left behind, but the reunion is a shock to the senses. The friend who stayed on Earth is now much older, their hair turned gray, and their face lined with the passage of 20 years, while the traveler remains young, vibrant, and seemingly untouched by the decades. This is not a trick of the mind or a failure of the biological body. It is a physical reality, because the traveler moved through space at such high speeds. They literally moved through less time than those they left behind. At this point, you might find yourself asking if this is merely a beautiful story or if we have actual evidence that the universe behaves this way. The answer lies within the cold, precise walls of our most advanced laboratories, where laser beams, vacuum tubes, and flickering data screens work tirelessly to confirm the mathematics Einstein laid out over a century ago. We find our first witnesses in the invisible world of subatomic particles. Deep inside massive circular particle accelerators, scientists watch as sparks of blue light whiz around tunnels at nearly the speed of light. These particles are often unstable, designed by nature to decay and vanish in a tiny fraction of a second. However, when these particles are accelerated to 99.9% of the speed of light, something miraculous happens. Their internal decay process slows down significantly. They leave behind long, shimmering trails, surviving much longer than they ever could at rest. To the particle, time is moving normally. But to us, watching from the outside, their internal clocks have been stretched out by their incredible speed. If particles seem too abstract, we can look to the very clocks that define our lives. Scientists have taken sophisticated atomic clocks, vibrating with extreme precision, and placed them in different environments to test Einstein's claims. In one of the most famous proofs, a glowing, humming atomic clock was placed into the cargo hold of an ordinary airplane. As the plane flew high above the clouds at sunset, circling the globe, a second, identical clock remained perfectly still on the ground. When the flight landed and the 2 clocks were brought back together, the world held its breath. A slight digital discrepancy had appeared on the screens. The clock that had traveled on the airplane was behind the clock on the ground by a fraction of a second. When researchers zoomed in on that nanosecond difference, they found that it perfectly matched the handwritten equations Einstein had produced so long ago. This realization changes everything. It means there is no single giant clock in the center of the galaxy that keeps time for everyone. Instead, the universe is filled with billions of independent silhouettes, each person and each object surrounded by their own glowing bubble of time. If 2 distant stars were to explode, one person might see them happen at the exact same moment, while another person, moving at a different speed, would see one happen long after the other. We are living in a cosmic loom, where threads of light and time are woven into a complex, stretching fabric that warps and bends under the weight of motion. Time is not a rigid ruler. It is a river that flows at different speeds for everyone. But even as Einstein solved the mystery of light and speed, he realized his work was not yet finished. He would often walk alone on the bridges of Bern, looking up at the sky with a thoughtful and unsatisfied expression. He knew that there was still one missing piece in the center of the puzzle, a dark storm of gravity and acceleration that his current theories could not yet explain. Despite the triumph of his special theory of relativity, Albert Einstein found himself walking the lonely bridges of Bern with a heavy heart and a deeply unsatisfied expression. He had unlocked the secrets of time and light, proving that the world we see is far more flexible than we ever imagined. However, a massive puzzle remained with one glaring missing piece in the very center. Through that hole, a swirling storm of gravity and acceleration was visible, beckoning him to go deeper. He realized that a dark, shadowy abyss was opening up in the middle of the classical physics library he had spent his life studying, and he knew he had to be the one to cross it, to understand why Einstein was so troubled. We must look back at the giant who stood before him, Isaac Newton. For over 200 years, Newton's work was the ultimate authority on how the universe functioned. His old leather-bound books were filled with diagrams of planetary orbits glowing in white ink, depicting a universe that moved like a perfect mechanical clock. In Newton's world, everything was calculated, certain, and absolute. Whether it was a heavy iron ball representing gravity or a 19th century cannon firing a ball into the sky, the same predictable laws applied. Newton envisioned gravity as a mysterious, invisible thread connecting every object in the cosmos. He saw the moon orbiting the Earth not because of the shape of space, but because a thin, powerful bond held them together like an invisible rope. The most critical aspect of Newton's gravity was its speed. In his equations, gravity was an instant force. If you moved a mass in one corner of the universe, every other object would feel that change immediately, regardless of the distance. According to Newton's law, gravity traveled across the 150 million kilometers of space between the Sun and the Earth with a 0-second delay. It was as if a cosmic light switch was being flipped, and the entire universe responded in the exact same heartbeat. But for Einstein, this was a mathematical and philosophical crisis. He had already established a fundamental speed limit for the universe, 300,000 kilometers per second, the speed of light. He had proven that nothing, not an object, not a signal, and certainly not a piece of information could travel faster than light. If gravity acted instantly as Newton claimed, it would be breaking the most important rule of reality. Einstein realized that the dark curtain of information being pulled across the universe could not move faster than light. To illustrate this impossible conflict, Einstein proposed a terrifying thought experiment. Imagine the sun suddenly vanishing, leaving a dark hole in the center of our solar system. If Isaac Newton were correct, the Earth would immediately snap out of its orbit and fly straight into the darkness at the very instant the sun disappeared. The thread of gravity would snap instantly, and our planet would drift into a cold, starless void far away from its original path. However, we know that light takes time to travel. Specifically, it takes about 8 minutes for a beam of light to cross the distance from the sun to our eyes. If the sun vanished, we would still see it shining in our sky for 8 final golden minutes. We would be bathed in sunlight, even though the source of that light was already gone. Einstein's logic was simple but revolutionary. If light takes 8 minutes to reach us, how could gravity be instant? If gravity were instant, we would feel the Earth fly off into space 8 minutes before we even saw the sun disappear. This would mean that an effect happened before its cause was ever perceived, a violation of the logical flow of the universe. Einstein knew that gravity could not be a magical pull. Instead, it must travel as a ripple through the fabric of space, moving at a speed limited by the cosmic signpost of light. He began to see a mysterious carrier wave made of warped spacetime moving through the stars, carrying the command of gravity across the void at the speed of light. This realization marked the beginning of an 8-year mental struggle. Einstein had to find a way to reconcile his new laws of motion with the ancient force of gravity. He had to look beyond the 0-second delay of Newton and find the hidden geometry of the cosmos. He spent his days in the modest patent office in Bern during quiet, rainy afternoons, his mind racing to find the answer. He was looking for a way to explain how the solar system remains in perfect, clockwork circles while respecting the speed of light. He was no longer just a clerk examining electromagnetic patents. He was a man standing on the edge of a great abyss, preparing to jump into a new reality where space and time were not just a background, but a living, breathing fabric that could be pushed, pulled, and warped. He was about to replace the iron ball of Newton's gravity with something far more elegant and profound. As he sat in his 1907 office, a sudden eureka moment began to form, and his eyes widened with clarity. He was about to have what he later called the happiest thought of my life. It was a thought that would involve a falling man and the realization that gravity might not be a force at all, but an illusion created by the very shape of the universe. The year was 1907. Albert Einstein was still a relatively unknown clerk at the modest patent office building in Bern, Switzerland. It was a quiet afternoon, perhaps with a soft rain tapping against the window panes, when a sudden flash of insight struck him with the force of a tidal wave. His eyes widened with a terrifying clarity as he realized something so simple, yet so profound, that it would eventually rewrite every law of the physical world. He later called this moment the happiest thought of his life. To understand what Einstein saw, we must imagine a scene that feels almost surreal. Imagine a worker in 1900s attire standing on the edge of a rooftop. Suddenly, he slips and begins to fall toward the ground in slow motion. In our everyday experience, we think of a fall as a terrifying descent caused by the pull of gravity. But Einstein looked at the face of that falling worker and saw something else entirely. As the man fell, he looked calm and surprised because, in that moment of free fall, he felt no pull of his own weight. He was, for all intents and purposes, floating in a state of pure weightlessness against the backdrop of the building rushing past him. Einstein took this thought further. Imagine if that falling worker released a heavy iron hammer from his hand during the descent. In a world governed by Newton's old rules, you might expect the hammer to fall differently than the man. But in reality, as they both plummet together, the hammer would stay perfectly level with his hand. From the perspective of the worker, the world outside is moving, but the hammer remains stationary relative to him. It does not fall away. It drifts beside him as if they are both in the deepest reaches of empty space. This realization creates a bridge through time, leading us directly to the modern era of exploration. When we see a smooth transition to an astronaut floating inside a high-tech space station, hair drifting effortlessly in zero gravity, we are seeing the exact same physics at work. There is a common misconception that astronauts are weightless because they are far away from Earth's gravity. In truth, they are experiencing the same peace as the falling worker on the roof. The astronaut is not weightless because gravity has vanished. They are weightless because they and the entire station are in a permanent state of free fall. The International Space Station is constantly falling toward the Earth, but it is moving at such a high speed that it keeps missing the ground. Its orbital path is a glowing blue line that wraps perfectly around the curvature of the planet, allowing the station to move in a graceful, eternal fall. Einstein realized that being in free fall is physically identical to being in deep, empty space where no gravity exists at all. This led him to his most famous thought experiment, the windowless room. Imagine a split screen. On one side, we have an elevator in the middle of deep space, far from any stars or planets. On the other side, we have an elevator on Earth with its cable snapped, plummeting in free fall. If you were inside either of these rooms, you would feel exactly the same. You would float. Your tools would float. There is no experiment you could perform to tell which room you were in. But Einstein did not stop there. He flipped the scenario to look at the opposite effect. Imagine a futuristic rocket in the void of space, its engines firing bright blue flames and accelerating upward at a steady rate of 1 g. Inside that rocket, a person would feel themselves pressed firmly into their seat, experiencing a force that feels exactly like sitting in a chair on Earth. Now, imagine a person inside a room with no windows that has been dropped onto the surface of a planet. They feel their weight pressing down on the floor. Einstein's genius was in realizing that the person in the accelerating rocket and the person standing on the planet would have identical physical feelings. If the rocket accelerates at the right speed, the person inside cannot tell if they are racing through the stars or standing still on solid ground. This is the equivalence principle. It tells us that gravity and acceleration are two sides of the same coin. They are indistinguishable. In the grand architecture of the universe, Einstein saw two glowing scales, balancing perfectly, one labeled acceleration and the other labeled gravity. By proving that these two forces were effectively the same thing, he had found the golden key to the cosmic lock. He was no longer looking for a mysterious invisible rope that pulled objects together. Instead, he began to look at the very shape of the room itself. If acceleration could mimic gravity, then perhaps gravity was not a force at all, but a consequence of the way the universe is built. As he walked back to his desk in the patent office, the old world of Isaac Newton began to dissolve. The idea of an instant, invisible pull was being replaced by a vision of curved light and warped time. He knew that if gravity and acceleration were the same, then a beam of light passing through a heavy mass must also bend, just as it would in an accelerating rocket. He began to see a universe where clocks near a heavy mass tick slower, their gears turning through a thick, syrupy space-time. This happiest thought was the spark that would ignite the greatest revolution in the history of science, leading him toward a final beautiful geometry of the cosmos. The transition from 1907 to 1915 was not a period of easy triumph, but a grueling 8-year struggle that transformed Albert Einstein from a young clerk into a weary visionary. As the years passed, his face became a living map of the aging process, marked by the deep lines of a man carrying the weight of the universe on his shoulders. Overlaid across this montage of his life was an increasingly complex web of mathematics that seemed to grow more tangled with every passing season. He spent countless nights standing at a blackboard, his silhouette illuminated by flickering lamps as he stared at rows of erased and rewritten tensors. The intense mental strain was visible in his posture, his back bowed by the effort of trying to see what no human had ever seen before. Einstein was no longer satisfied with the simple idea that objects were pulled by an invisible rope. He began to envision a reality where a planet moves because it is rolling along a dip in a translucent cosmic sheet. Imagine a massive glowing star sitting in the center of a flexible fabric, its weight creating a deep, elegant curve that dictates the path of everything around it. This was a radical shift from the old laws of physics, replacing the idea of a physical force with the beauty of pure geometry. To describe this world, he needed a new language, one that could account for a 4-dimensional hypercube rotating slowly in a field of stars. He found this language in tensors, mathematical symbols that floated and interlocked in his mind, like the architectural blueprint of a grand cathedral. However, the deeper he went into this geometry, the more the universe seemed to resist being captured by ink and paper. He realized that this curvature of space also meant a curvature of time. He saw that a clock positioned near a heavy mass would naturally tick slower, its mechanical gears forced to turn through a space-time that had become as thick and syrupy as honey. This was not just a theoretical delay, but a physical slowing of the heartbeat of reality itself. Even light, the fastest and purest thing in existence, was not immune to this warping. He visualized a grid of light bending downward as it passed near a massive planet, forced to follow the invisible contours of the curved universe. The struggle reached its peak in the final months of 1915. Einstein was nearly exhausted, his mind pushed to the very edge of its capacity as he wrestled with the final pieces of his field equations. He was trying to balance the scales of acceleration and gravity one last time to ensure they were perfectly level. In those final, quiet moments of discovery, his hands were visibly shaking as he put pen to paper. As he wrote the final equations that would define general relativity, the ink seemed to glow with a soft white light, as if the universe itself was finally breathing a sigh of relief. He had finally turned the golden key in a cosmic lock that had been closed for centuries. The door was now open to a universe where gravity was no longer a mystery, but a beautiful manifestation of curved light and time. He had moved past the mechanical world of Newton and entered a realm where the massive curvature of space-time around a glowing star could be calculated with perfect, high-detail precision. The struggle was over, and the masterpiece was complete. With the final stroke of his pen in 1915, Albert Einstein did more than just solve a physics problem. He unveiled a new reality that was as beautiful as it was terrifying. The equations he left behind, written with hands that shook from the weight of discovery, acted as a bridge between the small, everyday world we inhabit and the vast, shimmering majesty of the cosmos. In this new vision, the universe was no longer a cold, empty void where objects were pulled by invisible strings. Instead, Einstein presented us with a breathtaking wide shot of the entire galaxy, a place filled with shimmering energy flows and drifting cosmic dust particles, all held together by the very shape of space itself. For over 200 years, we believed that planets were tethered to their stars by a mysterious force of attraction. But through the lens of Einstein's finished masterpiece, we see a much more elegant truth. Imagine a translucent cosmic sheet stretched across the darkness of the void. When a massive object, like a planet, is placed on this sheet, it does not sit on top of a flat surface. Instead, it creates a deep, graceful dip in the fabric of space-time. A planet is not being pulled by a rope. It is simply rolling along the natural curves and contours of this celestial landscape. Gravity is not a ghost-like tug. It is the geometry of the universe in motion. To define this geometry, Einstein had to look beyond our three-dimensional world. He envisioned a four-dimensional hypercube, a glowing geometric structure that rotates slowly in a field of stars, representing the inseparable union of space and time. This was the architectural blueprint of reality. It was a world made of tensors, complex Greek symbols and numbers that interlock like the gears of a divine machine. These symbols float through the equations, describing how mass tells space how to curve, and how space, in turn, tells mass how to move. As we dolly out from a single glowing star, we see the true power of this theory. We witness the massive curvature of space-time around it in high detail, a warp so powerful that it bends the very path of light. This curvature is what gives the universe its structure. It is what allows the stars to cluster into galaxies, and what guides the dance of the planets around the sun. When we look at the entire galaxy, we are not looking at a collection of random objects, but a perfectly choreographed masterpiece of curved light and time. This was Einstein's gift to humanity, a way to see the invisible. He showed us that we are not just spectators in a rigid universe, but participants in a fluid and dynamic reality. The ink on his pages may have dried over a century ago, but the truth it revealed continues to shimmer like the stars themselves, reminding us that the laws of nature are written in the language of beauty and geometry. We stand now on the edge of this vast, curved ocean, finally able to understand the breathtaking scale of the home we share among the drifting cosmic dust. For 4 long years after the completion of his field equations in 1915, Albert Einstein's revolutionary vision of the universe remained a beautiful but unproven map. He had dared to challenge the ghost of Isaac Newton, claiming that gravity was not a mysterious force of attraction, but a physical warping of the geometry of the heavens. While the mathematics was flawless, the scientific community demanded a sign from the heavens themselves. They needed to see the universe actually bending. The opportunity for this ultimate test arrived in May of 1919, during a rare and dramatic total solar eclipse. Einstein's prediction was as breathtaking as it was simple. If a massive star truly warps the fabric of space-time around it, then even a beam of light racing past that star must follow the curve. Imagine a grid of light passing near a massive, glowing planet or star. As it enters the region of intense gravity, it does not move in a straight line, but bends downward, rolling along the dip in the cosmic sheet. To prove this, astronomers needed to photograph stars that were located directly behind the sun. Under normal conditions, the sun's overwhelming radiance makes it impossible to see the stars near it. However, during a total eclipse, the moon pulls a dark curtain across the sky, revealing the distant pinpoints of light. 2 expeditions were launched to the farthest reaches of the globe, one to the island of Principe off the coast of Africa, and the other to Sobral in Brazil. The stakes were impossibly high. If the stars appeared in their usual positions, Einstein's theory would crumble, and the world would return to the clockwork certainty of Newton. But if the stars appeared slightly shifted, as if pushed away from the sun, it would mean that the sun's mass had physically warped the space-time through which their light traveled. The astronomers waited in the humid heat, battling clouds and technical failures, to capture a few precious minutes of darkness. When the photographic plates were finally developed and measured with extreme precision, the results sent a shockwave through the world of science. The light had indeed bent. The stars had shifted by the exact amount Einstein's tensors had predicted. It was the definitive proof that we do not live on a flat, rigid stage, but in a universe of shimmering energy flows and drifting cosmic dust that warps under the influence of mass. Suddenly, the 0-second delay of Newton's gravity was a relic of the past. The message of gravity did not travel instantly. It moved as a ripple in the fabric of space, limited by the cosmic speed limit of light. Einstein became an overnight global sensation, a man who had looked at the sun and seen the hidden architecture of reality. He had proven that the massive curvature of space-time around a glowing star was not just a mathematical dream, but the very way our universe breathes. While Albert Einstein's theories brought a new, glowing clarity to the universe, they also whispered of a much darker and more terrifying reality. His equations did not just describe the gentle paths of planets rolling along a dip in a translucent cosmic sheet. They also pointed toward regions of the cosmos where the fabric of reality is not just curved, but completely torn. This is the realm of the black hole, the ultimate consequence of general relativity and perhaps the most mysterious corner of our existence. Imagine a magnificent tracking shot of a massive black hole, its accretion disk glowing with a fierce orange light as it visibly warps the starlight around its edges. In our earlier exploration, we saw how a massive star creates a curve in space-time, but a black hole takes this to an unthinkable extreme. It is a mass so dense and a gravity so powerful that the curve becomes a bottomless pit. If space-time is a fabric, a black hole is the point where that fabric is stretched beyond its breaking point, creating a massive curvature of space-time around it in high detail. But the most haunting aspect of a black hole is not its darkness, it is what it does to the heartbeat of the universe. We have discussed how a clock near a heavy mass begins ticking slower, its gears turning through a space-time that has become thick and syrupy. Near a black hole, this effect reaches its absolute limit. As an object approaches the boundary known as the event horizon, time itself begins to stretch and distort until it almost ceases to exist. If you were to watch a traveler drifting toward the abyss, you would see their movements slow down to an impossible crawl. Their pocket watch would tick once every minute, then once every hour, and eventually once every century. To your eyes, the traveler would seem to freeze at the edge of the hole, forever suspended in a single moment of time. From their perspective, however, time moves normally as they cross the threshold into a place where the laws of physics as we know them begin to crumble. At the very heart of this abyss lies what scientists call the singularity. It is often visualized as a dark, crystalline surface representing the ultimate truth of space-time, vibrating with deep blue light as it remains ungraspable. This is the point where all the mass of a giant star is crushed into a single point of infinite density. It is a place where our mathematical blueprints fail us, and where the Greek symbols and tensors Einstein used to build his theory begin to spiral into nonsense. The black hole represents the final boundary of human knowledge. It is a cosmic loom where the threads of time and light are not just woven, but are tied into an unbreakable knot. It reminds us that while we have learned to measure the 150 million kilometers between the sun and the earth, there are still places in the universe where our rulers snap and our clocks stop ticking. We are left staring into the void, witnessing the breathtaking scale of a power that can swallow light itself, leaving only a shimmering energy flow of drifting cosmic dust at its borders. These celestial giants are not just graveyards for stars, they are the ultimate test of Einstein's masterpiece. They force us to confront the fact that space and time are not just a stage, but a living, breathing participant in the drama of the cosmos, a participant that, under the right conditions, can hold its breath forever. For more than a century, we viewed the universe as a silent, majestic stage where the drama of the stars played out in a vacuum of stillness. But Albert Einstein's masterpiece revealed that the cosmos is not a quiet void. Instead, it is a cosmic loom, weaving threads of light and time into a complex, stretching fabric that warps and vibrates under the weight of motion. Throughout our journey, we have seen how mass curves this fabric. But Einstein's final great prediction was even more radical. He realized that if space and time are truly flexible, then any massive movement in the universe should send tremors across that fabric in visible ripples that travel through the darkness like waves across a vast, silent ocean. To understand these ripples, we must return to the fundamental conflict between the old world and the new. Isaac Newton believed that gravity was an instant force, like a light switch being flipped that immediately affected everything in the universe. In that old vision, if the sun were to vanish, the Earth would snap out of its orbit in 0 seconds. But Einstein knew this was impossible because information cannot travel faster than the universal speed limit of light. He proposed that when the sun moves or disappears, the command of gravity does not travel instantly. Instead, a ripple starts from the sun and moves outward at 300,000 kilometers per second. Imagine a dark curtain being pulled across the universe at the speed of light. This curtain represents the limit of what we can know and when we can know it. If the sun vanished, the Earth would continue to be bathed in sunlight for 8 final golden minutes. During those same 8 minutes, the Earth would stay perfectly in its orbit, unaware that its anchor was gone. It is only when the ripple in the fabric of space reaches us that the Earth would finally feel the change and drift away. Einstein saw this as a mysterious carrier wave made of warped space-time moving through the stars, carrying the news of gravity's change across the void. These ripples, known as gravitational waves, are the heartbeat of the universe. They are the undulations of a flexible, rubber-like grid that is constantly being stretched and pulled. When massive objects like black holes collide or stars explode, they do not just release light, they shake the very foundations of reality. They send out a pulse of energy that warps the grid, ensuring that the universal balance is maintained. This fabric is as delicate as translucent silk floating in a void, bending and twisting under the weight of invisible events happening billions of light years away. For decades, these waves remained a mathematical dream, hidden within Einstein's tensors and blueprints. Scientists knew that if they could detect these ripples, they would be able to hear the universe for the first time. They looked for a way to measure the tiny, microscopic distortions in space that occur when a wave passes through our world. It required technology more sophisticated than any atomic clock and precision that seemed almost impossible. They were searching for a signal that was ungraspable, a vibration in a dark, crystalline surface representing the deep truth of space-time. Finally, after 100 years of waiting, we found them. We detected the chirp of two black holes colliding, a violent event that sent a ripple across the galaxy, eventually reaching our tiny planet. When that wave passed through the Earth, it physically stretched and squeezed the space we occupy, including the very buildings we stand in and the air we breathe. It was a literal manifestation of Einstein's vision, the moment when the carrier wave of warped space-time finally spoke to us. This discovery changed our position in the cosmos forever. We are no longer just looking at a wide cinematic shot of a chaotic digital grid. We are now listening to the rhythm of the galaxy itself. We can feel the tremors of stars being born and black holes merging, all transmitted through the shimmering energy flows of the cosmic loom. These waves prove that space is not just a place where things happen. It is a living, breathing participant that carries the history of the universe in its ripples. We have moved from a world of rigid lines to a reality of fluid, beautiful geometry that connects us to the farthest reaches of the star-filled void. As we reach the conclusion of our journey through Albert Einstein's masterpiece, we must look beyond the present moment and face the ultimate question: where is all this leading? General relativity did not just explain how a planet rolls along a dip in a translucent cosmic sheet or how light bends near a massive star. It gave us the tools to map the entire history and future of existence. Einstein's equations act as a cosmic, architectural blueprint, revealing that the universe is not a static, eternal painting, but a dynamic, evolving story with a beginning, a middle, and an inevitable end. For centuries, the world was viewed through the lens of Isaac Newton's clockwork universe, where space was a flat, unmoving stage and time was an absolute ruler. But Einstein's vision of a flexible, rubber-like grid changed everything. If the fabric of space-time can be stretched and pulled by mass and energy, then the universe itself could be expanding or contracting. When we look at the breathtaking wide shot of the entire galaxy, we are seeing a structure that is part of a much larger, stretching fabric. This realization led scientists to the discovery that the universe is indeed growing. Galaxies are not just moving through space, the space between them is physically expanding, like a translucent silk fabric being pulled in every direction. But what happens when the cosmic loom runs out of thread? Einstein's equations offer several possible fates for the final chapter of time. In one scenario, the massive curvature of space-time created by all the matter in the universe might eventually act like a giant cosmic break. If there is enough mass, the expansion could slow down, stop, and then reverse. Imagine the entire galaxy and all the shimmering energy flows beginning to collapse inward. The dips in the cosmic sheet would grow deeper and deeper until everything, stars, black holes, and time itself is crushed back into a single point of infinite density, a big crunch that mirrors the singularity at the heart of a black hole. However, modern observations suggest a different, perhaps more haunting, end. We see a universe where the dark, shadowy abyss of empty space is growing faster than ever before. Instead of a collapse, we may be facing a big freeze in this version of the future. The fabric of reality continues to stretch until the stars are so far apart that their light can no longer reach one another. The cosmic loom becomes a lonely, cold place where the drifting cosmic dust settles into an eternal darkness. The glowing golden barriers of light will eventually fade, and the gears of the glass clocks that once defined our reality will finally stop turning. Einstein's final field equations, which he wrote with shaking hands and a soul weary from mental strain, remain our only guide through this final horizon. They show us that we are part of a breathtakingly vast and complex mathematical lattice. We are small, fragile beings living in the time bubbles of our own making. Yet we have managed to decipher the laws that govern the birth and death of stars. As we look at the final breathtaking wide shot of the entire galaxy, we realize that our position in the universe is both insignificant and miraculous. We have used the Greek symbols and tensors of a patent clerk to look into the mouth of a black hole and to feel the ripples of gravitational waves from billions of years ago. We have learned that space is not a vacuum of stillness, but a living, breathing participant in the flow of eternity. Einstein's journey began with a simple eureka moment in a quiet office in Bern and ended by giving humanity the keys to the cosmos. He showed us that the truth of space-time is ungraspable but beautiful, a deep blue light vibrating in the darkness. Whether the universe ends in a final crush of gravity or a slow, silent fade into the void, we can take comfort in the fact that for one brief moment, we understood the geometry of the heavens. We saw the veil peel away, and for a few final golden minutes, we walked among the stars,